Okay, we're with this slight addendum to Class 6C, and really what this focuses on is the example, the filter drain example, which is in the notes. So that it's just a relatively straightforward question. So a filter trench is required, small rectangular, 30 metres by 20 metres car park, which drains to its longer side. That's the 30 metre side. The trench's fill material is a porosity of 0.3. The design infiltration capacity, including the factor of safety, so that's the small q variable, is 0.13 metres per hour, and the rainfall characteristics for the site are illustrated in the figure below. Design the trench and check that it can empty at the required rate. So that's about checking that it can half empty within 24 hours. Now, I don't run through that calculation in this presentation, but it's relatively straightforward, and the equations for that are in the notes, and you're using a 3D infiltration device. So we ran through this example in class, and the next couple of slides are just really pictures of the whiteboard. The rainfall data comes from this IDF plot, which is given in the question. We're using empty and rainfall here, but normally you would design this for M30. What you'll find is this format of data, an IDF plot, isn't that good for getting accurate results off. That's certainly what we found in class yesterday anyway, but we are where we are. So the first thing we did in class was looked at what we knew. So we know the porosity, we know the Q rate, we know the area, so that's the area drained, we know the length of our device, and then we estimate a width, 1 metre. And then the area of the base of the device, which is 30 metres squared. The perimeter, which we can calculate, a very straight line there, and then this constant parameter b, which is used to size the device, and that came out at 0.89. Obviously, when you're doing this, it's important that you're consistent with your units. Where you might fall down is that the depth here, the intensity here is millimetres per hour, whereas all the other length units are in metres, so be consistent. Then what I did in class was I picked a range of durations, ranging from the smallest I could get away with, and the reason the whiteboard looks a bit smudgy here is I started at 0.5 and that turned out I should have went a bit smaller. So I picked a range of durations, then associated with that I've got a range of intensities, as I say there, from the IDF plot. Then I calculate this parameter A for each of those durations, and that parameter is based on this equation here, which is given in notes, and it's also given in the question. So calculate A, which is this call out here, and then calculate Hmax step by step. What we're looking for is, if you look at the plot here, Hmax to rise and then begin to fall. What you're looking for is the peak value. So in this calculation here, Hmax comes out as 0.75 units for that meters, 0.62 for the duration of 0.5 hours, 0.59, so you can see that it's peaked at 0.62. So that's our Hmax. So Hmax is the depth of the trench. So I should have said that. And you select the deepest response you get from those calculations. What you find is the equation doesn't give you viable answers for these events here. The issue here is your intensity is quite low, so it's infiltrating into the ground just as fast as it's raining. So basically it's saying you don't need any filter trench depth at all. The thing to note here is that by plotting Hmax against duration, sorry I should have been clear there, against duration, is you end up with this curve, and like I say, in class we spotted that this point here was the highest point. But of course what the curve tells us is that it's not the highest point, is that the highest point might be in here, and that's not a data point that we've picked in the charts. The other thing that could happen in a calculation like this is you could pick 3 points. So just say, I'll change my colour of pen here to illustrate this. Blue. Just say by chance we picked that point, and that point. You might end up with a curve that looks like that. Well, obviously not quite like that. Hopefully the ones that go through the dots. So it can lead to a situation where you think, well, it's not peaking, it's going down. So perhaps your peak is somewhere in this region here, and you can't find it. And that's really just a function of the fact that you've used the wrong duration interval. So you have to be quite careful with that. If you're in an exam, I wouldn't get bogged down. I would pick a range of 4, 5, 6 different durations from somewhere quite small, short, sorry, through to quite long. Pick a range, do the calculations. If you're not getting a peak, just say that you've perhaps made an error, or perhaps you're missing something like I've outlined in the plot there, and then move on to the next question, because there's no point in spending 2 hours getting the depth of your filter trench down to 3 decimal places, very accurate and very, very proud of that, and only getting 10 marks. Meanwhile, the other 90 marks in the exam paper are lost. So prioritise. And it's like that with a lot of the questions, the numerical questions often in these papers, is that quite often the calculations are a little bit repetitive, so don't let yourself get bogged down in them. Okay, and that's the end of this short presentation. If only all my videos were this short, that would be good for you and good for me, I guess. But obviously we have to get through more detail than has been in this one. I hope you found this video useful. If you've got any questions, get in touch using the usual methods. Okay, I hope this has helped you. Bye for now.